In the previous video, we saw how to construct minimum spanning tree by picking a cut randomly. But in the Kruskal's algorithm, we are going to pick a cut in a certain way. Specifically, we are going to pick a cut which respect our set A or minimum spanning tree set by giving priority to remaining minimum weight edge. Let's see how this is done. Consider this graph. Initially, there are no edges in our set MST. So we can pick any cut which goes through edge with minimum weight. In this case, that would be the edge between H and G vertices. So we can pick a cut like this. And then we are going to add this edge between H and G vertices to our MST set or set A. So after this step, our MST set will look something like this. It only has edge between H and G. Next, we have to pick a cut which respects current MST set and goes through the remaining minimum weighted edge. So here in this step, we can choose a cut which goes through edge between C and I vertices, or a cut which goes through a edge between G and F vertices, because both those edges has weight 2. So you can pick any cut which goes through either of these edges. So let me pick a cut like this. And then we are going to add this edge between C and I vertices to our MST set. Now if we continue this way, we can easily construct our MST or minimum spanning tree. But the question is how to continue this methodology to a pseudocode so we can actually implement it. Let's see how we are going to do that. For that, we have to follow two simple rules. Here we have prioritized to pick an edge with minimum weight. So in our pseudocode also, we are going to consider edges in non-decreasing order or edges with minimum weight first. Then we have to check whether that edge is eligible one. From eligibility, what I mean is that if both end vertices of an edge can be reached from edges which already in a set MST, by adding that particular edge will only increase the total weight of the MST. So in such cases, we have to ignore that edge and go to the next remaining minimum weighted edge. Okay, to handle this situation, we are going to maintain a table which has vertices and mapped set. Now this set is different from our MST set, and initially we set all vertices set to its value, and then before adding edge to our MST set, we are checking whether the end vertices sets are same or different. If they are same, which means these vertices can reach from another path, so there's no need to add considered edge. So we are going to ignore it. Otherwise, we are going to add the considered edge to our MST set. Now, before moving into our pseudocode, let's perform this operation now. So here I have a graph. I'm going to apply the previous mentioned technique to find MST for this graph. So here we have a table which maintains the vertices and the current set that particular vertex belongs to. So initially all the vertices set has been set to its value. Okay, let's apply Kruskal algorithm on this graph. So here we are going to pick minimum weighted edge first. So it would be the edge between T and U vertices. Now before adding this T and U vertices to our set MST, we are going to check whether those vertices set are same or different. Now if you check T vertex set, it is T, and U vertex set is U. So these vertices currently belong to different sets. So we can add edge between T and U vertices to our MST set. And then we are going to union these set. By unioning, what I mean is I'm going to set both these vertices set to one set. So either I'm going to change both these vertices set to T or U. Let's say I have changed it to T. Okay. So both these vertices are now belong to set T. And we can add edge between T and U vertices to our MST set. Okay, let's move on to the next step. So remaining minimum weighted edge is edge between R and T vertices. So let's consider that edge. Now if you look at R vertices set, it is R, and T vertices set, it is T. So R and T vertices are belong to two sets. Therefore we can add edge between R and T to our MST set. So let's do that. And then we are going to union the sets which T and R belong to. So R is currently belong to R set, T is currently belong to T set. and notice that there are two vertices are currently belong to T set. So you can either change all these three vertices set to R or T. Let me change it to T. So R, T and U, all these three vertices are now belong to set T. Now let me consider the next remaining minimum weighted edge, which will be the edge between S and U vertices. S vertex is currently belong to set S and U vertex is currently belong to set T. Since those sets are different, we can add this edge to our MST set. So let me add it, and then we are going to union these sets. Now U vertex current set has three vertices, so you can either change all these three vertex set to S or S vertex set to T. Let me do it in easy way by changing S vertex current set to T. If you did other way around, you have to change R, T, U, all three vertices set to S. So currently we have four vertices in our set T. The next remaining edge is edge between R and S. But both R and S vertices are belong to set T, which is the same set. Therefore, we are not going to add the edge between R and S vertex to our MST set. So we are going to ignore it. So if you look at, you can see that both R and S vertex can be reached from different paths. So there's no need to add edge between R and S. So let's move on to the next remaining minimum weighted edge, which is the edge between P and R vertices. Now P is currently belong to the set P and R is currently belong to the set T. Therefore, we can add this edge to our MST set and of course union these sets together, which means this P vertex set will be changed to T as well. Now there are five vertices in our T set. The next and only remaining edge is edge between Q and S, which has value 15. Since Q vertex currently belong to Q set and S vertex currently belong to T set, so we are going to add that edge to our MST set as well. So this will be our final MST for this graph.